Okay, so welcome back. This is a continuation of part one after hopefully a nice break. In part one, we looked at some easy things first, three-way handshake latency, and then things got a little more complicated with expert info, overlaps, retransmissions. This is a summary of the things we discovered from part one. In part two, we're going to spend time on bytes in flight and congestion and round trip time to ACK. There's only 3 topics, but they're fairly complex. There's a lot of meat on the bone to chew through. And I think we might finish just a little bit early. I'm going to do my best not to run over because I know we've got lunch at 12:30, if I remember correctly. So I didn't get to tell you about RFC 130619 yet. So this is a request for comment, and I really would appreciate your guys' feedback on your, I think you do your feedback on your app, the SharkFest app. If you don't have the app and you haven't downloaded it, please get with me afterwards. You know, I'm really looking for feedback. Any and all comments. Is this too much detail? Is it not enough detail? Is the sequencing right? Does it flow in a way that makes sense? Is it timing, you know, should we do A before B or B before C? Any of your feedback. You guys are my pilot, you're my control group. So you're seeing this for the first time, and getting your feedback would be helpful to tune it up for the Europe session. And if you want to see the Europe session, then please, by all means, sign up for the Europe session and join us in Portugal. It's wonderful. Okay, so we know we're going to analyze some symptoms around downloading. It seems like this mic is louder than it was. Does it seem, I don't have any controls, I don't think. Do I have, no controls? Not good thing for a control freak, let me tell you, no control. So we're going to look at why does it take so long to download a 1.4 meg file. 16 seconds is a long time for me. So we're going to jump right in. We're going to continue with the same kind of cadence and visuals that we left part one when we were looking at fragment overlap. So let's jump into bytes and flights. So let's start with a review. What is the meaning of bytes in flight? Great. So the amount of data on the wire that has not been ACKed by the other side. And how is this metric related to performance? So the bigger the number, the more we're pushing through the pipe. The smaller the number, we're throttling back, and we're actually slowing down transmission. So a big number, good. Small number, bad. So it turns out, as you might expect from part one, things look very different on each endpoint. So the BIF number, I'm going to use the word BIF if that's okay. I was going to get a picture of Biff from Back to the Future, but he spells it with 2 F's. So the Biff values look very different, and we're going to walk through a number of comparisons to help drive this home. So first off, where is bytes in flight in the decode? If you drill into the TCP layer, you'll see under seek and ACK analysis, you'll see bytes in flight down here in brackets. And we said earlier, brackets means it's a derived metric that Wireshark is calculating on the fly. What is so wonderful about Wireshark, besides the developers, is you right mouse click on that field, say apply as a column, and now you've got a new column in your view, and it automatically gets saved as part of your profile. It's like super, super handy. So I've updated our view with bytes in flight over here. I think I have a, there we go. So we have bytes and flights added to our view. We're going to start by looking at the server side capture, and we're going to just kind of explore what we see about bytes and flight on the server side. So let's first do some simple math around how bytes in flight is calculated. And before we do that, I should just go back and notice, if we notice that the numbers are going up, going down, going up, we're going to seek to explain that behavior. So let's do that. So first off, some simple math about how it's calculated. So we saw in our first segment on that screen, I didn't point it out, but trust me, there was a segment of length 3876, and when that was transmitted, bytes in flight was calculated at 3876. In fact, if you'll bear with me, let's just make sure we show that. So here's the packet, number 33, TCP length 3876, bytes in flight 3876. So that's what we're going to use for our math example. There's the wings that show the bytes are in flight. Okay. So then an ACK comes in. So we're ACKing up to saying my ACK value of 4345, which means, hey, I've received everything up until 4344, and I'm ready for 4345. So if we were to put some color around that, the green indicating, I think you can see that from the back, the green indicating, hey, this has now been acknowledged, it's no longer in flight. Why? Because it's been acknowledged. And now we can adjust the BIF value with some simple math. So taking sequence number math, doing some subtraction, we get bytes in flight now at 1292. So far so good, right? It is pretty simple math. So now we're going to send another segment, this one a bit bigger, and when we send it, bytes in flight is going to go up. So we've got our original segment over here. We've got our new segment over there. We do the math basically from this right edge over here, 10804, to this left edge over here where we transition from green to red. We do that simple math and we get 6460. So every time we put more data on the wire, BIF goes up. When we get an acknowledgement, or when Wireshark sees, remember this is a Wireshark derived value, so Wireshark is doing the math here. So when Wireshark sees the ACK, we reduce the BIF, bytes in flight. Everybody good with that? Yeah? Okay, and here's another example of receiving another ACK. Notice this ACK, because of what we saw earlier, large send offload, this ACK is spanning those two original segments. So we've ACKed this part over here, and then we've ACKed this part over here. Again, another indicator that we see different things on different sides. So primarily, we've seen bytes in flight increasing, right? Going up, going up, going up, going up. Uh-oh, it went down, and then it went up again. So just out of curiosity, what are some thoughts around why did it go up initially and then drop? A little louder. So data is being ACKed all along the way, right? If you see, I think I'm trying to change my pointer. Does that work? There's supposed to be like a laser pointer. Maybe that's that. So you can see 0 byte packets that are ACKs, right? So things are being ACKed all along the way. What's different, and yet we're still going up over here, what's different is there's two ACKs in a row that just coincidentally happen to arrive at the same time. Right, this is a server-side capture. We're interpreting the field based on what's in this capture. And we just happen to see two ACKs come in. We add a little bit of payload. Like, it's interesting that the TCP length does change over time. You know, at the app layer, the app is making decisions about how much to stuff in buffers and to send to TCP. But anyhow, it pretty much goes up, and then it goes down, then it goes up again. So you would expect to see, key point, you would expect to see BIF changing over time. And when you're looking at the sender side, you're seeing the maximum bytes in flight at any given point in time based on that capture. Make sense so far? Heads nodding? I'm going to skip that timing just for a minute. Let's jump over to the receiver. So now we're on the receiver capture up here. And notice bytes in flight is very different now. First off, we've got segments coming in that are, 1292. So that's the effect of large send offload. And bytes in flight increments until we ACK it. So notice we're ACKing every other packet, just like we should. So in a healthy condition, right, we're going to ACK every other packet. So it increments, we ACK the fact that we've received these two segments, bytes in flight now goes down to 0. And this is what you would tend to see pretty much, qualified, always on the receiver side. Because in a healthy network environment where things are in order and there's no retransmissions, we would be ACKing every other packet. And bytes in flight would go up 2 segments, down to 0, up 2 segments, down to 0, up 2 segments, down to 0. Does that make sense? Any questions about that?
Yeah, so the bytes in flight from the client side, are those associated with the server?
Okay, so the bytes, so remember, we're looking at the client capture, so we're calculating BIF based on what we see in the client capture, yeah. And as we saw, the sender has got a whole different point of view about how much is in flight, right? Once the receiver acknowledges 2 segments, we really have no idea what's coming next. Could be 10K, 10 meg, 10 bytes, we don't know what's coming. In this case, this is a 1.4 meg file download, basically. I would expect to see, it's not an FTP, but it's sort of FTP-like, where I've got to move 1.4 meg across the wire. This one?
So the server is sending to the client, and we're seeing the bytes in flight go up.
Over time. And think about latency for a minute. We know we've got something like, let's call it 125 milliseconds round trip. So if the congestion window opens, I can burst up to the size of the congestion window, and then bytes in flight will go up accordingly until I start to get some ACKs back. What's a little bit weird, and by the way, we always find something that's a little bit weird. No matter what capture we look at, you're always going to find something weird. It's just the nature of the beast. But it doesn't help. It doesn't help that we've got large send offload turned on. I thought that was me beeping. I wasn't even backing up. It doesn't help our brains that we've got large send offload on, because that's not really what's being sent to the receiver. We already saw in the last session we're getting smaller segments of 1292 bytes. But when we look here, we see what's being sent to the NIC card. Now the ACKs that come back, like packet 34 here, is an ACK, right? And we're ACKing some payload, and then we're adding more payload, so bytes in flight ends up going up, not down. But I'm not sure, did that help answer your question?
Yeah, I just wanted to look at it again.
Okay. You guys need to do tangent control for me. If I go off on a tangent, bring me back. Gently, but bring me back. So we looked at the receiver, we saw two segments come in, we ACK it, BIF goes down to 0. So this is a little bit, not a tangent, it's a little bit extra information. So far, we've seen how BIF can inform us about network health and the congestion window. In theory, as BIF goes high and low, it's really reflecting the congestion window. Congestion window opens, as long as there's receive window, we can pump more data on the wire. But we can also get a sense, and I put that in quotes because it's not exact, it's like we will get a sense of how the sender is, how he's allocated send buffers and how those send buffers are being used and which TCP API features are being used by the application. Meaning, if you've heard of the terms blocking and non-blocking. Have you heard those terms about TCP, right? Which is basically synchronous, where I send and I wait before I can send again. Or I can send asynchronously, receive some, send some more, receive some, send some more. So let's see how we could potentially learn about the send buffer size, which is sometimes a bottleneck, sometimes. Let's see how we could use the BIF field to do that. So if we were able to find the maximum bytes in flight, that would give us a clue or a sense of how many send buffers are available and how those send buffers are being used. And that's a hypothesis on my part. I'm pretty sure I'm in the ballpark, but feel free to ask some more questions about it. So this chart, I'm not sure if this is helpful or not, need your feedback. What we're trying to show here is the relationship between three windows. The blue line being congestion control window, the red line being the receive buffer, which might be a little hard to see in the back. It's here in the middle. And then the green line is the bytes in flight. And the key takeaway from this is notice that bytes in flight will never go above, it'll track with the blue line. So each time the congestion window opens, we'll add a little bit more data on the wire, will burst bigger until we get to receive window max. And then we can't go higher than that because the receiver is saying, hey, my buffers are full, don't send me any more data. So I have to stop. Bytes in flight cannot go higher than the receive window. It also cannot go higher than the congestion window. So it's really blue and red are controlling green. And I'll pause there for a minute and say, does that make sense? Does that track with what you've been told in the past? I got a head nodding, yes. 2 more, 3 more. I need a max of 5. Okay, I got more.
So did the graph come out of Wireshark?
No, this is just a hypothetical math project. Right, so let's change the graph a little bit. Let's move the red line up. So receive window now is higher. Congestion control is happy and increasing, but yet bytes in flight is not increasing. So this is where you could infer that something else is holding back the sender from putting more data on the wire. And this is where you might consider it could be a send buffer issue. There could be something going on in the application where it's allocated, I'll make up a number, 16K of send buffers, and you never see more than a 16K bytes in flight. Even though receive window is high, congestion window is high, there's no observable reason why bytes in flight doesn't grow. So when you see this condition, chances are it's send buffer limits. And I want to pause there and see if that tracks with what you've heard before, or could it be something else? I'm not aware of anything else it could be. That's why I'm picking on send buffers. So what do you guys think? Any challenge? Seems reasonable?
Well, I mean, it certainly can be, a send buffer issue, like what you said as well. It could be application buffers. It can also be congestion, getting data from, say, storage out to the network. So there's just so many things that can impact that number.
Yeah, so if I could repeat what you're saying, it could be like it's taking time to get data from a back-end server, right? Which is true, and I think that would impact response time. But in terms of if I have data to pump on the wire, and sometimes that data isn't big, right? If you're doing, I don't know, RDP or you're doing Telnet or something like that, it'll never be high because there's never any application data. So let's qualify that with you've got big data to move, like an FTP or something. And the buffers, I think when the app calls TCP to establish a session or an interface, I think it has to declare what is the send buffer size, how many buffers are available. And when you put that stake in the ground, I think that's what you have to live with. And hopefully it's a big number. So I wanted to bring that up because we're looking at bytes in flight. We saw it from the server, we saw it from the receiver, and I wanted to add on, but we can use that number also to infer something potentially about send buffer. And I do remember working in engagement where we were doing a data center migration or something, and whatever this third-party product was doing data transfer, it would never get higher than 8K. Might have been 16. It was a low number, and it turned out it was the send buffers. Okay, so how can we find the maximum observed bytes in flight? What's a simple thing we can do to find out in this whole capture what's the biggest number? Sort the column, right? Make sure there's a column, and then sort it. So if we sort by bytes in flight, we'll now see, and remember to scroll up. Sometimes I forget to do that. Sometimes I'm in the middle of scrolling and don't know it. So remember to scroll up. And in this particular case, it looks like 23K ballpark was the maximum I was able to achieve for one reason or another. And you can see it just by sorting. So we also have to assume that the network is healthy, that it's not being impacted by congestion window, and that the receive window is higher. I didn't actually check that for this example, so I need to go back and check that. But if we make those assumptions, then that limit might give us some clues about send buffer. So if it's really a mystery, why can't we get more data on the wire? Don't rule out the send buffer until you check this. Or the send buffer is guilty until proven innocent. Just like the network team. Do you guys have that? Guilty until proven innocent? Tangent alert. What's really interesting is some of our SaaS providers figured out how to be innocent until proven guilty. That I don't understand. But if you check like contracts, somehow you have to prove to them that it's their issue. End of tangent. Okay, there was something a little bit odd about that last screenshot that we had up with the decodes. And I want to look at that again and dive into it a little bit. So what was odd about it, and this is on the sender side. Earlier in part one, we looked at the receiver side. Now we're looking at the sender side. And the sender side, and let's just double check, server side shifted. So that's the sender's PCAP. Sender side is saying, hey, I'm transmitting things out of order. And I looked at that and I said, wait a minute, what? How can it be out of order? You're sending it. You shouldn't do that. That's naughty. So I want to drill down into that a little bit with you guys. Notice that we're still sorted by bytes in flight. So we're going to change our sort so that we're sorting by frame. So let's do that. We're going to take a quick detour about out of sequence. We're going to see, how can this be? Why would this happen? Let's resort it. So now we've got our same connection. This, by the way, this is the same connection from part one. So we've got our same connection. We're now sorted, hopefully, by this column. Should I put the magnifier back on for the back room? Yes, please? Okay. I think I did it. That better? Okay. So we're now sorted, and when we look at this screen with the color, somebody said earlier one of the great things about Wireshark is color. So when you look at the color, what jumps out immediately without even thinking about it? Sorry? Scary colors. Trouble in River City. Do you guys know that song, Trouble in No? Nobody? Anyway, it's a popular American saying. There's trouble in River City. Yeah, so the colors tell us there's a lot of expert info detection of errors, warnings, etc. And you can see a variety of fun things, right? You can see duplicate acts, you can see fast retransmissions, out of order, and this is all on the server side, the server capture, and the out of orders, let's just follow those over, see who's transmitting. So it's the server who's sending, and it's being flagged as out of order. Not really supposed to happen that way. Let's examine this a little bit more. So we're going to kind of zoom in and look at different frames. I think I have some speaker notes in here. I'll see if I can if I've memorized them. So we're going to start looking here at next sequence number 161. These numbers got big, I'm afraid. 1616554. So just think of 554. So that was kind of the last good payload. The reason I started there, it's not highlighted, it's white, right? It's no color on it. So that's the last good payload in this area of the capture before things start to get bad. That's why I wanted to hone in there. And then notice what comes immediately after that is a duplicate ACK number 3. So that's a interesting signal. And we're on the sender capture. So what would we expect to happen after that duplicate ACK number 3? A fast retransmission. So there's the fast retransmission immediately after that. And if we look at that sequence number ending in 5652, I think I'm going to anchor on that a little bit. Whoops, come back. I think we had to jump here for a minute. Let's go back here. What I want to do is I want to get to where it says out of order here, because that's kind of where we're headed. And the out of order help screen, which is, we looked at this in part 1, kind of gives us the order of precedence of how we flag things. And notice that RTT is involved, sequence numbers are involved, and even more important, this out of order condition can supersede retransmissions. And spurious, some words you just can't say. Spurious. Thank you. Retransmissions. So the reason I wanted to highlight that, and the reason we took this detour into out of sequence, right? We always see strange things we don't expect to see. Sometimes they're strange things of our own making because we're not looking at it from the right perception, the right perspective. So how does expert info do what it does? Well, it has to interpret the data it's given. And it's using some rule-based, I don't know the details, but some sort of rules to make choices about how to flag things. I'm calling those rules heuristics. Not sure if that's technically accurate, but it's in the ballpark, right? It's not artificial intelligence, it's rules-based. They're generally pretty good, but they're not perfect. They can't be perfect. If you relied solely on expert info, you might incorrectly conclude the wrong conclusion. Like, hey, the network is really, really, really bad, 3 reallys, when it's just 2 reallys. Network is bad, for sure, but human interpretation is the key. So it's important for us as people using Wireshark to somewhat trust but verify, is the term. Like, yeah, I trust it, but let me just double check it. Like, be from Missouri. You guys know the Missouri slogan? The show me state, right? I'm from Missouri. So there's nothing evil here. It's just be aware of it. What does torque me off, though, just so you know a little bit more about me, is someone who is getting started with Wireshark on our team. They print expert summary, info summary, they give it to the customer to say, here's your problem. It's right here in this report. It's like, no, you can't do that. You have to verify. Okay, back to BIF. So that was our tangent into out of sequence. We saw it on the sender. It doesn't really make sense to see out of sequence on the sender. They were actually retransmissions. But out of order trumps, I promised I wasn't going to say that. Out of order takes precedence over certain types of retransmissions. So let's look at the receiver side. Remember, we're looking at bytes in flight. We're trying to understand the maximum value. So again, simply sorting by the column header, descending, remembering to scroll back up. We can see a different number here, but at 20K instead of whatever it was, 23, 24K. But what's even more surprising to me is why is it ever bigger than 2 segments? Right? In our earlier example, we saw the receiver receive 2 packets, acking them, BIF goes back to 0. Receive 2 packets, acking them, BIF goes back to 0. Well, we're up to like 15K, 18K, 20K, and we'll just double check. We are on our client. So it's like, well, that doesn't make sense. What's going on there? How could they, why would the receiver ever see bytes in flight more than what I've actually received and acknowledged? Can you say it again?
The application is not actually processing the data fast enough?
So the comment was the application is not receiving the data. We're not handing it to the application fast enough, if I heard you correctly, yeah. So I wouldn't say that, because bytes in flight really is separate from handing off. Remember, bytes in flight is bytes transmitted that haven't been ACKed. So I think what this is, and I think a good way to look at it, is this is sort of the impact on the receiver for things that he's received but he cannot ACK, because they're received out of order, or I'm waiting for a retransmission. Well, mainly because I've received them out of order. So it's a little bit confusing. When we drill down, when we double click on this, I'm afraid it's going to get a little more confusing. And if anyone has the secret code, please tell me. So receive side maximum bytes in flight. Didn't quite look like what we thought it would from our earlier example. So let's look at how bytes in flight gets calculated when there's packet loss or out of sequence packets. So here's one example where we've got 2 segments coming in back to back. Notice that prior to the first one, that bytes in flight was at 0. So we have a value for the first one, but we don't have a value for the second one. Notice it's blank. So I've received data, but I did not increment bytes in flight. And it has something to do, I can't explain it, I haven't had a chance to talk to any of the developers yet, but I think it has something to do with the fact that the previous segment was missing. So it's almost like, hey, I received something, it's not what I was expecting. I'm not really sure how much could be in flight because there's something missing. I mean, you could do the math. I think we could figure out how much is missing. But just notice, be aware of the fact that, all right, for this segment previous segment not received, there's no bytes in flight number associated with this payload at that sequence number. Make sense? I mean, I shouldn't say it doesn't make sense. It doesn't make sense, but be aware of it. That's my goal, is to make you aware of it. And then we immediately send a duplicate ACK, and then another 1292 comes down, and we do increment BIF for that. We do declare it's out of order, but there's still no accounting for that segment there in terms of the BIF value. So I'm a little bit confused right now about how it's being calculated and is it being calculated correctly. So we did an increment. We're going to do something that's a little painful on the eyes. We're going to do a side-by-side comparison, top to bottom, with server on the top, client on the bottom, and we're going to try to just align what we're seeing in the top one with the bottom one, and just do some comparison. So split brain comparison, what's happening on each host. So to get started with that, we're going to anchor our comparison on that sequence number, 732782. So I've highlighted it in the server capture, I've highlighted it in the client capture. This was the easy part, just finding the sequence numbers. It gets a little more odd from here, as you might expect, because why? Because we have at least 120 milliseconds of latency between these two hosts. We have out-of-sequence packets, we have packet loss, we have signaling going on that from one end that the other end won't see for another, not round-trip time, but one-way time, because it can't get there. If you and I are if we're 60 milliseconds apart, you won't hear me until 60 milliseconds after I talk to you. Kind of like my cell phone discussions when I'm, as an AT&T subscriber, talking to somebody on Verizon. Sometimes that happens. Okay, so we're anchoring here. First thing to notice is server said, hey, I sent 3876. Client said, I only received 1292. We explained that. That's the large send offload. Notice bytes in flight in the top is 13165. Should I zoom? Sorry, guys in the back. Bytes in flight 13165 according to the server. Bytes in flight 1292 according to the client capture. So already we've got some things that don't line up, that's hard to explain, hard to understand. Then when we go to ACK, so after receiving this 3876 payload, we're ACKing this value, 726077, but down here we're ACKing something very different. We're ACKing 735366. So you can't just look at the order of things and interpret the order in terms of packet order, because they're reflecting different things on different endpoints that are far away from each other. And this is why I'm such a big fan of visualization, because trying to get to this level of detail hurts my brain. So before let me just ask. So we're trying to compare left brain, right brain, seeing what's happening. That last exercise it hurts my brain. I don't know about you guys, it just hurts. And I've been in scenarios where I'm trying to figure out a performance problem. I get both captures and I'm going, shit, how do I put these things together, right? And it's hard. So we can compare based on the sequence number. We can look at lengths. We can look at what's getting ACKed. We can look at BIFs. These things are not added. They're not synchronizing. We can recognize that there's packet ordering difference. And when we think about when something is happening, it's almost impossible by looking at lists of decode packets and have your brain consume it. Now there's supposed to be another half of this. Where's oh my gosh. So there's part of his head that's supposed to be exploding off. It's got to be the projector. So anyhow, yeah, so it's hard. That's the point of my exploding head icon. So we really need to use visualization if we want to understand really complex performance problems and why they're occurring and what's in scope of the investigation. We need to be able to visualize it. So we've seen some details about how Wireshark counts bytes in flight. We've seen some consistent behavior. We've seen some inconsistent behavior that we can't explain yet. We'll go to the developer den after the session and ask. And we've seen the challenges of side by side. So what I want to do now is kind of show you a technique that just makes this a whole lot easier. Because I'm all about easy. So we're going to talk about merging. And what if we could take those two client captures and merge them together, not simply by sequence numbers or by timestamp, but actually merge them together with some context and create some kind of high fidelity global picture and model of what's going on between the endpoints and TCP and the payload and everything else. And if we could enable some advanced analytics and we could fine tune the send time, receive time. In part one, we said if I know one number, I can estimate the other. If you merge captures, now I know both numbers. I don't have to estimate anything. So no estimating required. What if we could explicitly identify this packet was sent and never received with certainty, because I got both captures? What if we could accurately measure congestion and server response time? Because I need both endpoints to get those numbers right. So what if we could do all of that? So you guys, anybody remember this episode of Star Trek? Mr. Spock is doing a mind meld with the captain. So merge, I tried a couple of variations of this title and none of them worked. Merge, which we're talking about merging, melds the split brain. Because we're here to talk about split brain, but we're going to bring them together now by merging. We're going to bring both halves together. And I saw this when I Googled and I could not resist it. I had to put this up because when I saw it, it was just too funny. Okay, Star Trek 2019. Okay, this merge that I'm talking about is very different than merge cap. Anybody use the merge cap command line utility? Right? It's got some great uses, especially if you want to reassemble different captures, different points in time into a single, but it doesn't do what we're talking about. In fact, I tried merge cap for this course just to see would it give me something that I could share that would be meaningful, and what it gave me was a lot of retransmissions because a lot of the same stuff showed up. So what I'm talking about is very different. So we're going to go back to our visualization and we're going to add to it a chart and I think there's orientation. So here's some quick orientation. We're now looking at a file that's not a packet capture. It's a merge of two captures that are put into something called an application model. So you can't save this out and then load it into Wireshark because it's got two parts of the story merged together with some heuristics and analytics. So it's a merged file. We're looking at a time series chart now of bytes in flight. So whenever that number changes or stays the same, we can chart that over time and then overlay it with the traffic exchanges in the bottom panel. So we got a time series chart. We have some pop-up windows with details about problems, like we have this frame 998 was dropped. How do we know it was dropped? Because it's in this capture, but it's not in this one, and we merge them together, so we can tell that immediately. And then when it gets retransmitted, we can call that out. And this is a fairly clean view, and this is zoomed in pretty tight. Like the time period we're looking at is about a little less than 2 seconds of time. And we're going to zoom out and zoom in and share some details. But the interesting thing, the useful thing, what I find helpful is being able to look at bytes in flight overlaid with actual traffic moving back and forth between the hosts over time. So let's look at that a little bit more. So just looking at the bytes in flight chart, and you see a upward slope. What does that tell us? Sorry, say again? Increasing. Bytes in flight is increasing, and why is it increasing? Network's performing okay, everybody's happy, we're going to open the congestion window a little bit, right? When it drops to 0, what does that tell you? So all outstanding payload has been acknowledged. There's nothing on the network. When that number gets to 0, everything that was sent has been received. So there's no throughput. We're stalled. When it hits 0, nothing's happening. And it's a little bit of a offset, but if you go straight down, you'll see the ACK that got BIF back to 0. And in this case, the sender is the controlling end for BIF, right? Because the sender is sending, we're waiting for acknowledgments. When that acknowledgement comes back, we can declare those segments have been received, or that segment those stream bytes have been received. And in this case, there's nothing else outstanding, so BIF drops to 0. And then as soon as payload is sent, we can send some more payload. I got to steady my hand. I have not been drinking yet. Steady my hand, and then if I go straight up, now we can see that, yeah, this payload that's been sent is outstanding on the network, BIF goes up. When you look at the delta of this peak right here, this steady on this peak, and then this value, and they happen to just be 18K and 9K, what does that tell you about the congestion window and what is happening in the stack of the sender when you see those numbers like that? Well, so we went down to 0, right? So BIF doesn't really tell us about packet loss. It tells us about what's in flight. And it also, the what's in flight is representative of the congestion window, which we can only observe. There's no number for it. We can only observe it from the traffic. So when you see it go from 18K to 9K, some mechanism on the sender says, I'm not happy with the network. I'm going to shrink the congestion window by half and see if it helps. I'm going to reduce load on the network and see if the network gets better. Right, because TCP does two things, does lots of, but main two things: deliver in order and don't overrun the network. Right, so how do we not overrun the network? When we detect it's unstable, we don't put more data on it, we back it off. We back off, putting more data on the. So if you've been to the congestion classes, this should have been a topic, or it will be a topic, of when the sender decides the network's not stable, we're going to cut the congestion window by half and see if it gets better. And then we're going to cut it by half again, and then eventually we'll go into slow start. Does that contradict anything you're expecting to hear? So this is a great example of that expected behavior. I tried to do a BIF chart with Wireshark, and I need to go back and look at other ways to do it. I sat with one of the developers and said, am I doing this right? Is there a better way to do this? I was trying to get something that looked like this, but, that looked like the time series chart, but I was unable personally yet to figure it out. It's my mission to go back and see if I can do it and collaborate some more with the team and say, am I able to even do this? Does it do what I want it to do? Part of it is the y-axis, there's choices of min, max, average, count, and that's not what we're trying to show with BIF on this screen. Here we're showing the constant value until it changes. But I would love to be able to do it also in Wireshark to get that same perspective. Questions before we go on to timing? Is that view of overlaying a statistic with the traffic exchange, does that give you insight? Like give you a sense of things that you've not been able to get before? Is that good? I know when I started with like a sniffer and then a network general and then etherreel, and then when I saw that visualization, it's like, oh my God, I need that. Especially if you spend a lot of hours troubleshooting, right? Okay. So we're going to look a little bit about timing. We're going to look at timing a little bit. We're going to get rid of the BIF chart And we just want to kind of observe how long does it take for the sender to learn that a packet's been dropped? What's the cost? What's the penalty of a packet drop with this much latency in the path? So when does the server hear the news about the packet drop? So we can see it was dropped here, and we can see it was retransmitted over here. So this is a little bit similar to how we ended part one, but it's a different section of the capture. Similar behavior. So if you remember part one, we ended with looking at how long it took to get a retransmission recognized and then across the wire. So one of the first things I wanted to point out is, for the network engineers, this packet that was dropped, I don't know, I saw the pattern and I said, all right, well, it's at the end of the train. Could that be a tail drop? Maybe. If it is a tail drop, might I need to look at some of my queuing strategies on my network devices? Maybe. Just thinking out loud. Remember, it's a cluster, right? It's got VPN equipment, I've got internet. So there's a lot of things that we don't have control over. But if you see things that look like a tail drop happening in an environment that you control, you might be able to influence that. Does that sound right for the CCIEs in the room? Right? Weighted red and that kind of stuff. Okay, so it looks like it could be a tail drop. Here in this red direction, we've got two of the duplicate ACKs showing up. And then this next red area, so let me back up. So we got two of the duplicate ACKs, but we're able to still put payload on the wire because we have not yet learned from that third duplicate ACK, we haven't yet learned it never was received. So there's not a reason yet to shrink the congestion window. So we put more payload here, we put more payload on the wire, send it back to the client. I want to make sure that makes sense to everybody that we did that. Even though we lost something earlier, we haven't found out yet. We haven't heard the news yet. Because why? Because there's latency in the path. And it takes time to signal. And we had to actually signal in two different bursts, because in this burst, when we wanted to tell the sender that something's missing, I could only do, because of the nature of the payload and the bursting and the packet sequencing, I could only do two of the three duplicate ACKs. So the third duplicate ACK is in this downward trend of red, and then as soon as it's received, we retransmit it, and then we kind of have to wait, because things are so bad now, we need to wait for that to get acknowledged before we put more data on the wire. So two of the duplicate ACKs, there's the third duplicate ACK. And now we can kind of visually see, well, what was the cost? What was the cost of that packet being dropped in terms of time? Because remember my initial troubleshooting symptom? It's taking forever to download this 1.4 meg. It took 16 seconds, and I'm not patient. I'm not a patient person. I want this download done because I got stuff to do. So we definitely got issues with performance, plenty of bandwidth. Here's part of the reason why. So how long did it take to signal I dropped a packet? And the answer is on the screen. So from this point in time, when the sender sent it, that's sort of like the starting point in time, right? Put it on the retransmit queue until I hear about an ACK. And then finally that ACK, the triple duplicate ACK comes, and I'm able to do a fast retransmission, but even then I don't know if it got there until this time point. So it basically took, I'm going to say 1, 2, 3 round trips to figure out that a packet was lost and to make it right. Does that make sense? Do you guys see the same 3 round trips? So round trip time of 120 milliseconds times 3, right, for one packet. And if we do a lot of those, then John waits a long time for his download. because of packet loss. So we're seeing the effects of, in this merged capture, where we bring the brains together, we're able to visualize in more detail the impact, what's happening, why it's happening, and the impact. Any questions about that before I go on? Okay.
So to do this, you need to be able to capture in both locations.
Yes, and ideally filter out all the noise and put just what's relevant from both sides. Sorry? Filtering, yeah. I mean,
To be able to, when it happens, yeah, you did it.
now I happen to always run a capture on my laptop. Because weird things happen. I'm in hotels, airports, airplanes, whatever, and weird things happen, and I want to look and see, well, why did that happen? What was the reason? And I tell customers who buy, they're customers, so they buy our stuff, I tell them, deploy capture agents, host-based capture agents out to all your hosts. It's free, it doesn't cost anything, and you always have packets when you need them. Because that's one of the worst things of you're trying to troubleshoot and you don't have the data, right? Somebody comes to you and says, hey, last Tuesday there was an issue, can you see what you can see? It's like, no, last Tuesday's gone, it's history, it's toast. Anyhow, any other comments, questions? Before we move into congestion?
What host-based capture agent that's free that you're talking about?
So you can configure Wireshark to do continuous capture in a wraparound buffer, right? You could do that. Since you said the word free, that's the answer. For a little bit more than free, there's some other solutions, but this is not a sales pitch. This is a technical deep dive. So we were drilled into a 2-second time period earlier. We were like micro-focused, and we were seeing traffic moving in bytes and flights. I've zoomed out now just to kind of show you what the entire connection looks like visually. There's no decodes on the screen, right? There's just patterns and colors and stuff. So we still have BIF up here. We have our packet exchanges down here. This is, about a 5-minute period. But I want to zoom into this part of the picture. So I just select that part of the picture with my mouse, right mouse click on it, say zoom in, and then it zooms into that part of the capture, the merged capture file to show, all right, for that thing that you just selected, let me see the details. And what you can see pretty clearly is that during the time, so BIF on the top, packet exchanges on the bottom. If you see blocks of, like here, if you see a block, that's a histogram saying, there's a bunch of packets in there, half of them have no payload, the other half in blue, the other half have some payload. And then on the top, you can see a pattern of BIF going up, coming down, going up, coming down, going up, coming down. So what's that called, that pattern? Say it again. Oh, it's a sawtooth pattern, yeah. So what does that sawtooth pattern tell you about TCP? What is TCP doing when we see that pattern? It's shrinking the window and then gradually opening the window and shrinking it and gradually opening it again. And that starts with the letter S, ends with the letter T. What? Slow start. So that's the answer I'm looking for. So this is an example of the penalty that you pay for packet loss on a large network and the impact on bytes in flight. Because remember, bytes in flight is your throughput. In essence, it's not exactly your throughput, but if bytes in flight is low, your throughput is low. If bytes in flight is high, you're doing a good job of filling up the pipe and you're getting some pretty decent throughput. So kind of notice that whenever it drops down, there's some flags for frame drops and retransmission. So just like what you would expect the way TCP was designed to work, when the network becomes unreliable, the congestion window shrinks. We're going to slowly test it to see if it can handle load because conditions are always changing. And if it seems to do okay, we'll increase it a little more until it gets bad, and then we'll shrink it again. Make sense? Any questions, comments? So again, we're looking at both sides merged together. High fidelity in terms of packet loss, for sure. It's not suspected loss, it's real loss. And accurate BIF values. Another aspect of that visual is some advanced analytics that does some delay analysis. And the reason I put this on is because of that BIF up and down and slow start. For the 16-second period of time where I was waiting for my transfer, it's called out about, I'm going to say 75% of the total delay is all TCP related. So TCP timers, waiting for retransmissions, delays in signaling, all that stuff. And then there's a little bit of congestion and a little bit of bandwidth delay. We're going to jump into congestion next. So BIF for receiver side doesn't really tell you much about the actual congestion window because the receiver doesn't know what's in the pipe. It only knows what it's received. The sender knows what's in the pipe. So BIF on the receiver isn't really a reliable metric. I'm not saying never look at it, but just be aware of what you're looking at. Segmentation offload is, it's a great feature. It does wonderful things, but when you're trying to do troubleshooting, it can create some challenges for us as practitioners. And then as you can see, packet loss on a high latency path is pretty severe impact on performance. So we finished BIF. We're done with BIF. I've updated the spreadsheet with just the stuff we talked about for BIF. And I was going to say we should stand up, stretch a little, say hello to the person next to you, but don't leave the room because we're going to start again. Shake out your legs. I don't know if you guys remember being in kindergarten, but wasn't that a great time? Right? They'd make you stand up, roll on the floor, jumping jacks, take a nap. No naps yet. We just have a few more minutes for nap time. Then we'll have a nice lunch and then take a nap. So, I'm a big believer in stretching. I was going to put on here, it's a stretch break, but please don't break anything. Just stretch. Okay, are we ready to move into congestion? We've got 30 minutes. I think this will take 27. So we're going to move into congestion next. Did I miss a slide? No. So remember, this. We looked at this slide from part one of comparing the connection handshake, and we noticed the client had 121 milliseconds, the server reported 129, and we said, okay, this is a point in time, there could be asynchronous paths, there could be several things impacting, making these numbers different. Let's start with what is the definition of latency? And I think we're going to get a couple different answers. So please contribute your definition of latency. The time it takes from point A to point B. Excellent. Anything else?
Composed of network, application, server, client, the different pieces that comprise overall latency.
Excellent. So there could be different components to latency. We're on a good track. We're on the right track. This is what I wanted to hear. Anything else? Okay. What's the definition of congestion?
Not enough room to put something else in.
The bag is full.
The bag is full. The highway's full. Too much traffic.
So elaborate on that.
It's a point of transmission where you start dropping packets.
Okay. Congestion might cause packet drops. So how about, I'm going to give you a definition to consider. I'm not asking anybody to change their mind. But consider a definition of congestion as things that are, it's a delay that's not latency, not server, not application. It's the thing that is the delay when it's not something else, and we're going to explain that, what I mean by that. But in general, if you boil it away, it's like queuing in the network. I might not drop a packet, but it might be in a queue longer than necessary, and it's not, and it's different than end-to-end speed of light latency, right? Because end-to-end speed of light latency should not change. Even if you can take a measure at sunset and a measure at sundown, it still should be the same. So we're going to look at how can we tell the difference between latency and congestion. If I have congestion on the network, there might be something I can do about it. If I have high latency, true path latency, there's probably nothing I can do about that. If we're talking about speed of light, I can't do anything about it. Distance is distance. So you could define congestion based on what it isn't. So it's not protocol delay, so it's not ACK timers and retransmit timers and things like that. It's not serialization delay, like how long on a 100 meg, 10 meg, 1 meg. Based on the link speed, and you've got to put data on the wire, there's a serialization delay. You know, if it's 1 meg, you can only put 1 meg on. If you got more than that, you got to wait per second. May not be server delay, and I put maybe, because we do see queuing going on inside of ESX hosts. So if our definition of congestion is queuing, it's possible ESX could be involved. And there may be some others, but it's not the ones that we said it's not. So can you think of something else that it isn't, that congestion as a delay is not in another category? Trying to pull out other. I think I got most of it here. Let me keep going. So I want to introduce, and there's probably another term for this, one-way total transfer time. One-way total transfer time. And there's probably other names for that. You might say half of round trip time. But round trip time is latency plus congestion, and I want to be able to segregate out congestion. So it's the time required for bits to leave the sender and arrive at the receiver. So not really thinking about application layer or servers, really interface to interface is what I'm thinking about. TTT, total transfer time, it's one way, so 1W total transfer time. One way total transfer time. So how might you calculate that? So it's the total transfer time that you observed, interface to interface, minus bandwidth delay and latency delay. And when you do that math, the number that you're left with is congestion or queuing delay. So a delay that's not latency and it's not protocol delay and it's not bandwidth delay. And I have a super simple graphic that might help to make this easier. So this is a totally exaggerated example. Forgive the simplicity. Bandwidth of 1,000 bits per second, just making the math easy. Latency, big number, 5 seconds. And we know that we transferred data that took a specific amount of time, interface to interface. So we could say that the bandwidth delay, and I think what I'm missing here is a file size. Darn it. We could say that the bandwidth delay we know based on that link speed and the file size, it took 30 seconds to serialize the bits onto the wire at 1,000 bits per second. Right. At 1,000 bits per second, I can't put it on the wire any faster than that. It's fixed speed. And then if we were to add in the latency that we know, that we've determined, that we believe is correct, those two numbers, but that doesn't seem to add up to the total transfer time. There's still something missing. And that missing piece is the congestion delay. So when it's not bandwidth and it's not latency, and it's, again, interface to interface time. So we're not thinking about server response time. This is all network. And the reason we want to focus on the network is if we find congestion, we as network owners and engineers and operators might be able to do something about it, maybe. Does that help at all? Total time minus bandwidth delay minus latency. What's left that you can't account for in any other way is queuing delay or congestion. So round trip time is not the same as total transfer time, because round trip time in Wireshark also includes delayed act time, retransmit timeout time. We'll see some examples of how that's calculated. Unfortunately, Wireshark can't tell us a lot about total transfer time because you need both captures to really measure it accurately. You can't measure it from one capture because you don't know when it got to the other side. If you have both captures, you know when it got to the other side. So when we look at round trip time or round trip RTT-ACK, round trip time to acknowledge, it turns out that it's actually giving us also protocol delay. So protocol delay here. Oh, I have to fix something. I'll do that on the next version. It'll be even better. So in the case of looking at round trip time, we have to also consider that Wireshark will include protocol delay, and there's some examples of that coming up. Okay, so how can we find congestion with Wireshark? Not easy, but we can get some insight, for lack of a better word. We can get some insight. And we can use the RTT to ACK, round trip time to ACK, and then make some inferences about what we know about how it's calculated. So we're gonna take a look at that. It's not perfect. You'll get a decent approximation, right? If you're off plus or minus 10%, that's okay. You'll at least have a sense for, is it actionable or not? But protocol delay could be our downfall. And so we have to know how to interpret it. So that's what we're gonna look at. So I'm going to speed things up a little bit. We've got 15 minutes. RTT to ACK is included in the seek ACK analysis section of TCP. It's calculated there based on time deltas. You can apply it as a column, and then you have it in your view. And in some cases, it's tempting to say, well, it looks an awful lot like a display delta. It almost matches almost every time, but it's not the same. It's a different measure. So we've got our column. We can sort on that column, which would give us, and if we remember to scroll up, that's my note to myself. Then we can see, in this case, we're looking at server side. We can see that, well, the highest value of round trip time to ACK in this capture is 342 milliseconds. Now it's a little bit weird because earlier we thought latency was around 120 round trip based on the three-way handshake. That was the only information we really looked at. So you might say, well, if latency is 120, 122 or whatever, and round trip to ACK is 342, that means there's a lot of congestion. You might infer that, but what we're going to discover is this number also includes a lot of protocol delay. So we're going to zoom into packet 15 here in a second, I think. Yeah, there's a zoom in a bit. We're going to explore packet 15. So if we look at the server-side capture, we see the 342 number, and we just have to say, wait a minute, how can that be? We figured out that latency was 120-ish. What the heck? Why is that happening? And if we look closely at the packet sequence, what we're going to see is we're going to see that packet 14 was some payload from the server, 151, and that's all it sent. It only sent one packet. So then we finally get an ACK back, but we only sent one packet. So when will the receiver send an ACK if I only send one packet? You guys know this. I know that you know it. I just need to tease it out of you. You can do this.
After the next
would be if there was a next packet, but there's not a next packet in this scenario. Say it again. Of a specific timer. You're on the right track.
It's waiting for the next packet. If the next packet doesn't come, then it needs a certain timer and then it will send the next.
Exactly. And that timer is called the delayed act timer. So what we're seeing here is this number includes the delayed act timer. I mean, it has to, it must, it can't not. The universe depends on it. Sanity depends on it. So if we were to jump to the client side, and we've just put the client side on the bottom, same sequence of packets, we're comparing endpoints, and we zoom in, we can see, okay, let's go back, 389 payload, nothing else came in. Notice the delta time is 209. So in the receiver side, we see a 209 delay. In the server side, we see 342. Why are those numbers different? Because, who said that? Yeah, so the server includes not only the delay from this TCP stack, but it also includes the transfer time. That's right. So again, the topic is congestion. How can we see it? It's not easy to see with Wireshark, but we can infer some things if we can rule out some things. So I don't know what that's called in scientific method, but it's really a matter of ruling things out in order to kind of see what's still left ruled in. So client says 209, server says 342. So the reason is, and the round trip time was the answer, server is saying, well, it took time to get to the client, to the receiver. Then there was the delayed act timer waiting for that. And then it took time for the act to come back. So delayed act timer was 209. If we add in round trip time, we're in the ballpark. Everybody agree we're kind of in the ballpark? So now the next question, what's the smallest latency we've seen so far? It's kind of the opposite of the maximum. If we were to look at the smallest, we'd be able to know what was the minimum round trip time observed in this entire capture, and we might infer, well, maybe that's actual latency because it's the minimum. It's no guarantees, but it's a reasonable, excuse me, it's a reasonable guess or a reasonable data point. So let's kind of visualize what we just saw with those two round trip times. So from the server perspective, down here on this, the bottom of the swim lane, from the time we sent the packet right there to the time that we got the ACK back right there, 342 milliseconds, so you can see that it does include the round trip time. And then from the standpoint of the client, it's really just the delayed ACK timer, the 209 milliseconds. By the way, this is, you don't need a merged capture for this. This is one of those measures that you don't need to merge. So we're trying to put congestion in a context that's different from our first round of definitions where we were talking about latency. We're trying to make it special and different so that if we could detect queuing delays, which is not latency, it's not protocol delay, if we could detect queuing delays, we might do something about it, right? If we own the network equipment, we might be able to figure out what box it is. So it's a good indicator of an actionable result. Right? We don't always find actionable things. We find lots of crazy things, some of which are actionable. So what I was going to do now, and there's not going to be time, is I was going to spend more time on latency, but I think we're going to have to skip over a couple of additional latency examples. Otherwise, we won't finish in time, and I'm hungry. Are you guys hungry? Yes, sir.
So, typically when I see queuing delay, it's looking at the delta time column
Okay.
on the client side, and then the delta time column on the server side. And if, your delta time's jumping into the milliseconds versus being in the microseconds,
So there's certain cases, depending on where you actually capture and how much latency is in the path, and if there was no latency at all and no delayed act timers and things like that, then the display delta, which by the way is how I started this section, and then I realized, oh no, I really should have been using RTT to ACK because it is different, and it does include the protocol delay. But you know, looking at it the way you did is valid in certain circumstances where you know all the, you know, the conditions, especially low latency. So I really want to be respectful of the time, and I'm going to skip ahead a little bit to another visualization, because when you merge the captures together, you're able, because you can see exactly when things were sent and received, you're not having to guess, you can see congestion. So we're very quickly, this is like 3 slides, I think, 4. We're looking at the merge again. So this is that same merged file. And we've got the entire capture displayed. You know, you can see the burst of packets, et cetera. And then we can overlay that with a different metric. Earlier we did bytes in flight. You can overlay any metric. In this case, we're overlaying packet congestion. And notice that there's 2 directions. So because we have both captures, we can see if there's congestion in one direction, the other direction, or in both directions, because we've got everything we need to make that determination. So blue is congestion going from the client to the server, and red is congestion going from server back to the client. And here where you've got this bar, this histogram, you can see, okay, this is our download. We had 16 drop packets, we had retransmissions, and oh, by the way, we had a fair amount of congestion occurring during that same period. And if I kind of look at the scale, it was in the ballpark of 100, peaking out at 100 milliseconds. But if we drill down into this segment of the capture, just, you know, select it, drill down on it, now you've got more details about when congestion was occurring. Now, again, this is not latency. This is queuing delay, other congestion occurring on the network that was impacting transfer time. And then in terms of how much was it impacting, like this spike here, this is like 100, that top one is like, if I look to my left, it's like 100 milliseconds on top of latency. So I mean, there's some serious congestion and some serious queuing delay going on during the time of my capture. So earlier we saw packet loss out of order. Now we're seeing one of the reasons for packet loss and out of order, which is congestion, right? Things are getting thrown away. They're coming out of different devices in the wrong order, etc. So back to that same delay analysis chart, the blue wedge represents any delay associated with pure congestion. So it's not huge, but it's enough to be annoying. And, you know, would love to get with my network guy and say, why is my VPN connection so slow, Chris? And I won't tell you what he told me. I want to, but I won't. So anyway, there we go. So that, by the way, he said, don't use New York anymore. It's a bad thing. It's a bad concentrator. Don't use New York. Use Durham. It's like, okay, thanks for telling me. I appreciate it. Hi, Chris. So why is there so much congestion? Because it's a complicated network. There's multiple tunnels, multiple protocols, multiple ISPs. My server's on an ESX host that could be oversubscribed. It could be starved for CPU or memory. It could be swapped out and waiting to get resources, right? That's never good. And I've got a VPN client on my laptop. There's certainly overhead associated with that client and what it has to do. Put packets into tunnels, take them out of tunnels, proxy the connection. It's doing work, right? Okay, so any surprises about the amount of congestion? And it's pretty ugly. A pretty big mess. And I was trying to be a productive employee that day. Imagine. And I couldn't. It took me 16 seconds. Congestion can occur in both directions. And I'm hoping that by looking at it this way, that it kind of helps explain how congestion can impact performance in ways that are different from server delay, and different from speed of light latency, and different from protocol delay. Right? If we can separate those things out, we can boil down to something that we might be able to do something about, like don't use the New York concentrator. Hi, Chris. I hope you'll still talk to me. We can edit that out, right? No, not a chance? Okay, so we looked at round trip time to act. We looked at congestion. Really, the congestion, I mean, honestly, it requires some advanced analytics. You can kind of infer by looking at, I mean, and the gentleman in the back has done some of that, and that's probably as good as you're going to get is doing that manual. So there it is. We finished our marathon. We split our brain into two parts. We did part 2 and part 1. We looked at lots of different conditions. My experience has been it can be a lot confusing, especially with high latency. It's great to have both captures. If you can filter them and use them, you need to split your brain. And we couldn't do what we're doing without Wireshark, and it gets you to a great point, but then there's an extra kind of mile that you may need to deal with in more complex scenarios. And that's where visualization can help, and advanced analytics like the delay analysis. So we looked at these things in part 1. We looked at these things in part 2. I'll upload the spreadsheet. Like I said, any final questions or comments? We have 3 minutes to lunch. Helpful, interesting, insightful, good use of time? Yeah. Then I hit the target. All right. Well, thank you, everybody.